All right. So, hello everyone. We're gonna get started. Thank you for coming. This is the ICAL seminar series, the last session for Christmas break. We are very fortunate to have a host, a guest that is not longer at here in the UK, but has been doing great work into many relevant fields. Team Pearce has worked very long at GameAI and the machine intelligence teams at Microsoft Research. And he's going to give us a very holistic view into both imitation learning and world models, which are very key techniques if you want to have truly agentic and embodied systems. Thank you, Tim, for your coming here and looking forward to hear from you.
Cool, awesome. Yeah, hi everyone. And yeah, first thanks to Christos for finally getting me here. I think we've been speaking about doing this for about a year already. And yeah, also to Antoine for hosting me this afternoon. Really appreciate that. So yeah, I was thinking hard about what to speak about today, and I kind of condensed it to something like on this slide. So I think going back like 6-7 years, we were seeing like kind of interesting results start to appear in very specific domains. So there were some very cool like policy learning things that were being done in simulation, and there were like very early signs of like model-based RL starting to work well. And you fast forward to like the last year or two, and suddenly we see these like amazing demos of things actually starting to work, both in the real world on the policy side, and on the world modeling side. We've suddenly taken this big leap from like these very fuzzy, blurry pictures of like low resolution environments to like suddenly these like interactive, like real-time world models that are modeling complex games or even like reality in some ways. And so what I've tried to do in this talk is really to compress, as I see it, like the key kind of insights and milestones that have like taken us from that sort of 2017, 2018 phase to like starting to see some of these things work in the real world. And so I'm going to be stepping through these like 5 insights. It's a bit of a personal story as well. I'm obviously going to be talking about the research I've done along the way. I think some of these insights I've been pretty good at like catching on to, and I think some of the others I've only really like realized them in retrospect. So yeah, some of these I have kind of more played a little part in, and others I've like just been following along like everyone else. Okay, so first I want to talk about at a really high level what has been going on and what has changed there in like the past 5 years as I've seen it. So going back to kind of mid 2010s, a really exciting paradigm in machine learning research was deep reinforcement learning, right? So this was aiming at this setting where you have an agent acting in an environment in this like sequential manner. And yeah, there were some cool things coming out of this. But it was like a very, like the philosophy at the time was very much like, let's create a general learning algorithm that can be plugged into any environment we can give any like reward function to, and the agent will figure out how to solve this. This is a super hard thing to do, right? Like essentially what you're asking the agent to do is go out and like collect its own data set. And that data set is going to be specific both to the environment and that reward function. And like really because of this like complication in what you're asking the agent to do, you end up needing like a lot of let's say a lot of like you have problems like stabilizing your learning algorithms. So your data distribution is changing over time, so you need to start thinking about like clipping your reward functions, doing some like trust region type thinking of like you want your policy to change but not too quickly, and then you have all this like sea of things around this that get built out, like your Q functions, your value functions, your advantage functions. And there's like 1,000 different ways that you can piece these things together. And like people were spending a lot of time exploring this stuff. On the other hand, we've had like in many ways a much simpler paradigm like emerge that was not really in this, originally it's not really addressing this like interactive framework, generative AI. So this was like looking at, primarily it came from like vision and language modality, and the ingredients to this look very different, right? So it was now, rather than having an agent or a model like collect its own data set, it was much more about, let's like lean into this like human generated or at least human curated, mass amount of data out there already. And because you now have this like fixed data distribution, training becomes much more stable. And the objectives that we have are essentially generate this data. So either you're doing the next token prediction thing in language, or you're doing something like generate the image from the text. And so as I see it, like a lot of like what I've worked on and a lot of like what has started, the techniques that have started to work in these like robotic applications and these world modeling settings are really taking ideas from this generative AI paradigm and like applying it to this kind of sequential decision-making loop. I think more recently we've seen increasingly, as well as just the modeling ideas and philosophy, we've actually seen the models starting to be passed down to this second loop as well. I've been, including in the title, I've used this word embodied AI. I don't know how people feel about that here. I'm looking for some kind of a word that means like doing this loop, but not necessarily doing like the reinforcement learning part, or philosophy of how to learn these agents. So that's what I'm using it for.
Not being a loop, but so far describing it for interacting with a world model doesn't really change that loop. What do you mean that the genetic AI is producing the model?
So what I'm trying to say here is that, so I'm not saying whether we're doing the world or the agent at the moment. I'm just saying that that what I've seen happen has been people have tried to treat this problem setting of like either learning the agent or the environment, but they've been trying to do this from more of this like generative AI mindset. Okay, and so the first key to like aligning these two things is like kind of getting a data set of behavior in these embodied settings. I started out kind of transitioning to this area of research through this paper, Counter-Strike Deathmatch with Large-Scale Behavioral Cloning. So this was never meant to be a paper when I started it. This was like mid-COVID lockdowns. Trapped inside for many weekends. And at the time, there were these Dota systems and these like StarCraft systems that had come out. And I personally played this game Counter-Strike, and I was like waiting for one of the labs to like build a like world-class Counter-Strike agent. No one was doing it, so I was like, oh well, let me have a go. It was a very different scale, of course. I think something that I really enjoyed about this project was it was kind of the first time in my PhD that after my PhD, where I'd like really been just trying to make something work. And I'd been like very method agnostic. Like I think early on I'd had these ideas of like, oh, look, I'm also going to do some types of reinforcement learning. And I've been doing Bayesian deep learning in my PhD. So I was like, I'm going to incorporate some uncertainty stuff into the agent somewhere, and like all these complicated things. But I think through the project, it's so hard to get something working in real life that you end up just distilling things down to like the simplest possible solution. And so I ended up landing on this behavioral cloning thing, which at the time was like pretty unpopular actually as a research area. And I remember like submitting this paper to a couple of like machine learning venues, and it wasn't really getting through review cycles. People were saying, well, what have you done here? Like, this is not interesting. But yeah, this has been like I guess a vehicle through which I started to get some of these insights. And I think in some ways we've seen the field move towards these like simpler ways of trying to get agents to do things. Now, the first I mentioned, you really need to align these two paradigms of generative AI and reinforcement learning is to say, well, okay, let's start from like an offline static set of human expert data. And so this is, yeah, serving a little bit as the framework for the talk. So yeah, we're going to assume we're in a setting where we have access to a human demonstrator, and we can observe them. We can watch them, and we can collect the observations that they're receiving from the environment, and we can look at the actions that they're applying to the environment. So in the Counter-Strike case, this is you get a snapshot of the game, and then in the next split second, you can see like what where they move the mouse, did they click the mouse, press some keyboard buttons. Okay. And so ultimately you get this data set of observation and action tuples. I say offline-ish, actually. I wanted to talk about that for a second. So I think these data sets are never, they're offline like 99%, but you know, when you're building one of these systems, you don't go away and you say, I'm going to do the full data collection. Okay, I've got the data. Now I'm going to train the model and then write the paper or whatever. Like, there's always some iteration. You know, you get 10% of the way through your data collection and you train a model and you kind of see, okay, it's sort of working, but like, it's not really doing very well at this part of the map or in this task. And so you start to like influence your data collection. So I think even though we talk about this as like, yeah, learning from offline data sets, I do think there's kind of a critical detail there of like, we do end up like shaping the distribution of data that we're collecting through this process. Okay, so insight 2 here is that given you have this data set of observation and actions, there's like really 2 simple objectives that I think make most sense in this context. And this is super simple, right? So one is you predict the future action. The other is you predict the future observation. And you know, if you're predicting the action, this is doing behavioral cloning. You are building a model of the human demonstrator. If you're predicting the future observation, conditioned on previous observations and current action, you are doing world modeling. And you know, going back to this vision of like generative AI versus RL, I think these are like the kind of generative objectives that you could think of in this like sequential environment. Yeah, in terms of use cases, so obviously if you have you're learning a model of the human demonstrator, that's useful because you can now plug that model into an environment and get it to do things, which is good. I think with the world modeling thing, I did want to say something about this, which is, so world models have like grown out of this like model-based RL view of learning, of like we're giving the ability for how to, you know, understand how the world works to an agent, and it can do things like planning, it can do things like learning and imagination. I think what we're seeing in these sort of pixel generative world models that are actually coming out is like the use cases are not necessarily going to be that. I think the emerging use cases we're seeing are things like potentially these are like new forms of entertainment. You know, these are like fun to interact with. You know, I'm thinking of the Genie style models where, you know, you can be very imaginative with the types of worlds that you want to like explore. The kind of use cases in robotics that we've seen at least emerging first have been things for doing evaluation. So, you know, it's hard to build simulators of certain things like I don't know, cloth folding and this type of thing, but potentially having a world model is like a slightly more realistic way of simulating this stuff. And also, yeah, synthetic data generation. Okay, so yeah, we needed data sets. We have like 2 simple generative objectives. Insight 3 that I think really started to emerge like 2.5 years ago was like, what generative machinery should we use when we're training these models? So building back to this Counter-Strike project, I I came to dealing with the mouse space, and I had this worry that there were moments in the data where there would be like multiple things that a human would want to do. So maybe there's like a bunch of enemies that appear on the screen and you don't know which one to click on. Maybe you have, two pathways, et cetera, et cetera. And I spent a long time like experimenting with this, and I was trying to do like some like mean squared error stuff, and like that was kind of working, but there were like cases where it felt like it failed a little bit. I ended up kind of designing this like very domain specific like discretization scheme where you have like in like Counter-Strike, most of the time you're just like moving the mouse around like the middle of the screen. You're not really making big movements. So you come up with this sort of fancy binning scheme effectively, but you're like treating the X and Y then independently because you don't want to give your model, you don't want to confuse your model with too many options to choose from. Yeah, and I want to use an analogy here of like, well, what do they do in image modeling? So imagine this is a bit of a forced analogy, but imagine your observation is now like the symbolic digit that you want to produce, and the action is to generate an image of that digit. And so you have lots of nice demonstration data where there's like lots of different handwriting styles. And then you do something like how we used to do behavioral cloning, and you learn this like, fuzzy mean approximation of this behavior, which, somewhat looks like the things, but you're like missing a lot of it also looks like none of them at the same time. And so I think one of the projects I'm kind of proudest of having worked on was this imitating human behavior with diffusion models. So 2021, 2022, there was this thing called diffusion models that had just come out. And this was like a super stable way, at least relative to like GANs and things that had come before, to train image generative models. And I'd had this kind of problem in my head of like, well, we have like this issue with, with behavioral cloning, where we're kind of like doing these like approximate solutions. And so the idea really in this paper was to say, well, okay, what if we take this cool technology that seems to be working really well in images and like plug it into generating actions? So yeah, it's really as simple as that. So instead of going from text to images, which was everyone was starting to do at the time, we define this new setting where we say we're going to do observation to action diffusion. And yeah, on the bottom row here, we have some rollouts of like a robot starting from the same environment, random seed, and doing a bunch of different behaviors, which was kind of the point of doing this. Like we really want to capture this multimodality in the data. But I missed something actually. So although I'm like proud of that project, there was like a key detail that I ended up overlooking. So yeah, diffusion BC, that's kind of the method that we proposed, was doing diffusion on a single action. So this was like, given your current observation, let's output the next action that we want to apply to the environment. Of course, right? That's like the paradigm that we're in. I remember chatting with actually one of my co-authors at the time, Tabish, and he had kind of suggested like, oh, well, what if we output more than one action for like many time steps and we could do some impating stuff or something? And I was like, yeah, but we don't need it. We can just like, have the model output a new thing at every time. But yeah, this turned out to miss something. So diffusion policy came along like a few months later, and they, it was a very similar philosophy. It was like observation to action diffusion. But instead of outputting a single action, they said, no, we're going to output this chunk of T actions. I remember reading this paper and thinking, this is a bit silly. Like, we're only ever going to use one action at a time. But yeah, why did this end up helping? I think there's a few reasons I've heard people kick around. I think the ones I like the most are like the second one there. I think it is much more kind of natural in some sense to think about doing some kind of motor control in like say a half-second chunk rather than like step by step. So if you're going to like close a laptop lid, you're not kind of like moving along, stuttering along and like kind of thinking again what to do at each time. You kind of just say, okay, I've got to reach out my hand, and you sort of do it in one motion. I think the other thing is at the bottom there, which ends up becoming important when we start to plug these things into VLMs and create like these more modern vision language action models, which is, at test time, you have a limited number of like flops per second that your GPU is outputting. And, you could choose, you could say, I want to have a smaller model, do more updates. But like what seems to be much more effective is to say, well, no, let's have like a bigger model, do a smaller number of like forward passes per second. And this, seems to be like a better compromise in a way. Okay, so this is on the policy learning side, behavioral cloning. At some point, we also started thinking, we've taken this thing that was originally like working really well at image generation, and we've now kind of rewired it and figured out how to make it work for action generation. But, why not use it for what it was good at already? What if we just keep using diffusion to do this like world modeling side, to do this like observation prediction side? And so this was a project that started out as an internship with Edouard and myself, although he went back to his university and put a lot more work in it to turn it into like a very, very complete project. He did a great job on this. Effectively at the time, we were coming up with the sort of version 0.1 of how to use diffusion to do world modeling. So we were not doing any of the like, I think more recently we see world models that are more using like video diffusion type pipelines. At that point, we were doing this very simple thing of like stacking a history channel-wise and then concatenating also your current kind of noisy frame and then doing the denoising process on that. But actually, this kind of works pretty well for like simpler environments. And here's some clips of like the model that Edouard trained on this Counter-Strike environment. I think it's so cool that within the space of like 3 or 4 years, I went from like really struggling to like model the policy side of Counter-Strike to like being able to actually model the kind of engine side, like the actual game engine side of this whole thing. Oh, we lost one. We still got this one though, right? It's not too bad. And this was like relatively small scale. So I think Edouard trained this on like, I think 2 kind of mid-tier GPUs. But yeah, it was enough to like generate this like fairly modern game, and you could play like close to real time as well. Okay, so yeah, where are we at? So we've kind of got this insight of like, learning from static offline expert human data is good. There's these 2 kind of nice, simple prediction objectives that seem to play really nicely with this generative AI view of things. And then the insight 3 is that, using some of this like good generative machinery plays very nicely in these, both when you're generating actions and also the observation. So insight 4, like leverage pre-trained models. This is also something that was it's in some ways this is not a new idea, right? Like back from when people were starting to do like ImageNet training and taking like ImageNet models and then fine-tuning them on some other downstream tasks. Like people already start to get the idea that starting from foundation models is like a generally good thing. In this Counter-Strike work, I was relatively limited on the amount of compute I had available, And something I found was that like initializing this like efficient net with image net weights, even though it's a task that's not really anything to do with classifying different breeds of dogs, this was like really helpful to speed up the learning of the model. So on the right hand side, this is like, yeah, game score along with like hours of like high quality expert data. So you have random initialization, image net initialization, and then I have this purple line, which was like image net plus like some very kind of noisy CSGO prediction data as well. And then there was this paper that came out like not that long ago, actually, like, yeah, 2023, RT2. This was like another thing that I kind of got wrong. Like I remember reading this paper, and the core idea was that they were putting a language model at the heart of the policy, and then they were adding on this vision encoder, and then adding on some like robotic data as well. And I remember reading this and I was like, this is really dumb. Like, why would we want a language model as the core of this like model that's going to act and do things? Why do we need to have a model that knows things about coding and celebrities and like astronomy and all this like nonsense? But yeah, this turns out to be the template for the model for the modern VLA, Vision Language Action Model. And I think like looking back at the Counter-Strike experience as well, like I sort of thought of this as like, oh, this is like a nice way to get a bump in your performance, but I hadn't really digested like how significant this was. And actually this was like an important part of the whole pipeline. And so, yeah, I think, you see the amount of like success that VLAs have started to enjoy, like especially the last year or so. And so my thinking is like changed on this a lot since then. The way I think about it now is that, like, yes, an LLM might not, might have some knowledge that is like not strictly useful to everything you're going to be doing action-wise, but it has a lot of good stuff in there as well. So, for example, it knows at a symbolic level, like what is a draw, what types of things go in draws, how heavy are draws, how big are they, how do you like interact with them? It knows this in like a very like symbolic, cerebral way. Next stage in training these things, that they go from an LLM to a VLM, right? This is kind of the training pipeline at the moment. You start from an LLM, you put on a vision encoder, you train an adapter between the two things, and you mix in some vision language data. And so at this point, you have all this like symbolic knowledge about what a draw is, say. But then you're connecting that with like, okay, what does a draw look like? Like, what color are they? How to identify it within an image? What does it look like for like a door to be open and closed? Like all this type of things, right? So then you get that baked into the VLM. And so in VLAs, they're normally starting from VLMs and they're adding on this action head. And actually at this point, you can start to feel that actually there is like some pretty useful knowledge in these systems already. And really the thing that it has to learn to do is like, okay, output this slightly new language of like actions to execute a task. But yeah, this is the way that I've started to reason with myself about why these things are useful. Of course, another good thing about this is you get a very new functionality from doing this type of thing that almost comes out for free, where you can now talk to your model, right? You couldn't talk to the Counter-Strike model. There was no way to like get language into that. But now you have suddenly a way to like specify things in like a more vague way or a more specific way. You can start to use like the reasoning capabilities of these LLMs, and you can have the users like interact with them in real time. And these things are really like, yeah, these are some things we see come out in some of these robotics demos now, but really they're coming out for free as a consequence of using these like VLMs. I think the SEMA series of work is like a really nice example of this. SEMA 1 does this like, more kind of Counter-Strike agent type thing where they start from, they train their new model on this set of games. They use some like lightweight language embeddings and some vision encoders, but essentially they're kind of strapping things together. Whereas the SEMA 2 model, which come out recently, is essentially, let's start from Gemini and fine tune it on this video game data. Yeah, one extra way, not to labor this point too much. One other thing that really convinced me about the value of these systems are some kind of small scale experiments that I've done playing around with LLMs for imitation learning. So I think classically in imitation learning, we're in this setting where you have your training data, you have this training phase where you're like passing all that data into your model, baking it into the weights, getting it to learn this observation to action function, and then you freeze it, right? And then in inference, it's just kind of this fixed mapping, and then you go and roll it out in your environment. But yeah, there's this kind of emerging paradigm of like, sometimes people call it in-context imitation learning, where you take, literally a pre-trained LLM, GPT-5, whatever you want, and you just put in text, like, these are your action trajectories, these are your expert trajectories, this was the observation, this was the action, blah, blah, blah. And then you just ask it, you say, this is the new observation, what action should you do? And at least if you try to make this work, like, you have to do a bit of the prompt engineering stuff, but you can get decent performance. So this is, at least in simpler settings. So this is an example of GPT-5, doing this like 2D racing environment. It's definitely not this fast in real life. This is sped up kind of significantly. But yeah, this is, I think, another piece of evidence I have in my mind of like, okay, these LLMs, they do really have these kind of general like reasoning abilities like within them. And so like figuring out later how to like translate to like some new action modality, I think is, not too beyond them. Yeah, with the pre-trained model, I think one other thing I wanted to mention quickly was, I think on the world model side, we've seen this a little bit more slowly. But like, as I understand it, like 99% of the world model problem is video generation. And starting from like a good video generation model and adding in actions and maybe fine-tuning it to the specific domain that you care about, is like a very quick way to make progress here. Okay, so insight number 5, neural scaling laws hold in embodied AI. So this was like a very, in some ways, like a depressing lesson I learned from this Counter-Strike project. So as I say, like early on in the project, I'd had these ideas of like doing these like fancy algorithmic things and like doing some online learning, like rolling it out in the game. The thing I found like worked over and over again was just like making the data set bigger. Like of everything, of all the fancy things I would try, of like changing the way of like shaping the action space. These things would all have minor improvements that would add up to some degree. But the thing that really made a difference was this like boring thing of just like going and doubling your data, doubling it again, doubling it again. Yeah, I look back at this, I feel a bit bad using the large scale word in this title. I think the data set we were using for that was about 100 hours, which I think is, not too significant by today's standards. But yeah, that's why you join an industry lab. I guess one of the benefits is you get access to more data and more compute. So yeah, we had this paper, World and Human Action Models Towards Gameplay Ideation, which came out in Nature earlier this year. I'm not going to talk about too much of the details behind this, because I think other people would have spoken about this in the past at this series. But I wanted to talk about the scale angle of this in particular. So the core model that we trained here was a autoregressive transformer. We were doing the kind of VQ-VAE thing of tokenize your images, tokenize your action space, and just predict the next token. So in some ways, this is combining those two objectives. We're doing both behavioral cloning and also world modeling combined in one world model. I'll play a quick clip of, this is actually just one of the intermediate models coming up with this, generating this this environment. So it's like decent quality. So the model has like an idea of like physics of the game, like it drops down there. And then it also starts to like be able to model, like kind of imagine these interactions with like enemies in the game. But I think something that really stuck with me from this project was like, again, like how scale just made things better and better. So I'm going to play now on the left-hand side here. We've got this ground truth clip of like a human player playing this video game. So this is like a ground truth clip. They grab this item, they run up these stairs, and then they do this like jumping and flying animation. And it was like super interesting to see, just by adding more data and more compute to the model, that it got better and better at capturing this thing. So like early on in training, it would like survive for a second or two, and then things would start to diverge. After like 100K updates, it kind of things maintain, but it like missed the action collection, and at the end it like jumps, but the model doesn't quite understand what this flying animation is. And it's only after like about 1 million updates that where you start to see the object interaction was modeled correctly, and it starts to get this idea of like this this flying animation. And so it was really observing this that like led to a paper we presented at ICML earlier this year, Scaling Laws for Pre-training Agents and World Models, where we're essentially studying this like qualitative observation a bit more rigorously. And we do this both for the behavioral cloning side, that's the pre-training agents, and the world modeling side. The main question that we really wanted to answer was, is scale in these embodied AI tasks, do you think scale as well in embodied AI tasks as in language modeling tasks? So in language modeling, you have, we've known these things called scaling laws for a while, where if you increase your model size, your training compute, this loss just keeps going down in a very predictable way. And this has been like hugely influential in LLMs, right? Because it means that a lab can come along, Anthropic, whatever, they've trained one model, does pretty well, they're getting some users, and they really have faith in saying, well, okay, we're going to 5x, 10x the compute for the next version. And, they kind of know that things are going to get better. And so what we were able to find is that, like, yes, like you see these very similar patterns holding in these two embodied AI tasks, world modeling and behavioral cloning. Again, there's some details that I'm brushing over. You have to be a bit careful about how you structure your model. You also get slightly different shapes of these scaling curves. You'll see the BC curves are kind of plateauing a little earlier. But essentially you have the same things. Like you pour more data into these systems, you set the objectives right, you use good like generative modeling machinery, and things are going to improve like as you put more resources into the system. Cool. So these are kind of the 5 main insights I wanted to share today, and I want to spend a little bit of time talking about, okay, well, where does that leave us now? Like, are we done? Like, in a way, we have, as I was saying, we have these two recipes that like very reliably improve with compute and data. And I think what we're seeing now in all these demos that like appear on Twitter is like you have this like set of like super strong like robotic startups that are going out there and they're betting on this recipe working, and they're going in on the data collection, because that's kind of the big difference between where we are in embodied AI and where things have been in like LLM land, where LLMs, we were sitting on, people call it like the fossil fuel of AI, right? We were sitting on this like internet-sized bank of language data that was just like ready to be scraped and like poured into models. Whereas, in these like action-based settings, a lot of the like robots have not even been around for that long. like as long as the internet. So there's definitely not these like large data sets out there. And so I think one of the like important research is kind of becoming a research question at this point is like, how do we do this data collection? And there's various ways that I think we're seeing, yeah, these different robotic startups like placing bets on, do we do like teleoperation? Do we kind of like look over the robot's shoulder and do things? There's this kind of cool idea from Sunday Robotics of like having these sensors that like a human is kind of changing their hands into like a like robot form, and they're collecting like full like data about like what a human's doing. And so yeah, the way I see like a lot of the cool stuff happening in this robotic startup scene now is like people are placing different bets about the data collection strategy as well as the embodiment and the set of tasks that are going to kind of give them the most value earliest. There's like a slightly more researchy way of looking at this problem that I've been a little bit involved with. So we had a paper in Europe's, just presented last week, 2 weeks ago, which is to say, well, rather than having to actively demonstrate all this stuff, kind of using these robotic sensors, there are like bigger pools of data out there of like humans going about everyday tasks and manipulating things with their hands. And so if there is a way that we can like learn from this data, I think this offers an alternative way to kind of solve this data problem. Cool. And so I think my answer to like it's my own question, but I ask like, are we done? And it seems like, okay, if we collect enough data, it feels like maybe we're done with imitation learning for like the specific set of tasks that we are collecting this for. But I think I was thinking the other day about there was this talk by Andrew Ng. I kind of got into AI in like 2016, and I was like watching a lot of his lectures at the time. The deep learning like revolution was like well underway, and he had this story that he used to tell of like, he'd been around in AI for like whatever, like another 10 or 15 years at that point, and he was like, look, before deep learning came along, when people said they worked on AI, really they were like fiddling with how to get features from data sets. So given an image, like what kind of filters can I apply to like get good features out to then apply these like very shallow learning algorithms on top. And he was like, this is dumb, deep learning's coming along and we should be learning these features kind of end to end. And that's happened very effectively, right? I don't think too many of us are playing around with these types of feature algorithms anymore. And so deep learning has kind of eaten into this stack of like things we want to automate. And my perspective on like what's going on in imitation learning now, and I think LLMs more broadly, is I think potentially we're like hitting a new like local minimum where like if you look at like what people are actually doing, like where is the work going into these systems? It's effectively on the data side, right? So, I've talked a lot about the getting data for these to do behavioral cloning, something like that. But you see this in LLMs as well now. Someone finds out like, oh, look, LLMs are not very good at this type of reasoning task, or like this this ARC problem or MML, like whatever it is. People figure out there's something wrong with it. And then you get a bunch of other people coming along. They build some benchmarks around it. They collect data around that thing, and then they say, "Oh, look, now I can do the thing." But then there's like another hole emerges, and this is where we're starting to get this like problem of like this. People refer to it as jagged intelligence, where you're like really strong at one thing and then really weak at like something else that doesn't seem, that seems kind of related. And I don't think we've I think in embodied AI and imitation learning, I think we've always lagged a little bit what's happening in these other domains. But I think it'd be very surprising if we don't encounter the same the same issues with embodied AI, where we say, okay, well, we've collected it for these 20 tasks, but this 21st task that kind of looked similar is actually like not really learned for free like we hoped. And so, yeah, I think that the thought I really want to close with is like, maybe we're starting to be done with like the algorithmic side of imitation learning. There's still very much the data problem to be solved. But I think from the higher level, I think we're very far from being done with having systems that can learn in like a very general way. Cool. And that brings me to the end of what I prepared to talk about. So yeah, happy to take questions now, or I believe there's like a more informal kind of discussion afterwards that, yeah, we can also talk in.
So